Hey there, universe nerds. You've heard of black holes, places where gravity is so strong that nothing, not even light, can escape. But just outside that point of no return lies something equally fascinating and a little terrifying: the photon sphere, a region where light doesn't fall in or fly away, but orbits the black hole in perfect circles. It's one of the most extreme environments in the cosmos, where space and time are curved so tightly that even light, the fastest thing in the universe, is trapped in an eternal loop. Let's set the scene. Imagine approaching a black hole. Far away, light travels in straight lines. As you get closer, space-time bends more and more. Eventually, you reach a point where light from your flashlight would curve back toward you. That's how strong gravity has become. But if you move to just the right distance, exactly 1.5 times the Schwarzschild radius, the radius of the event horizon for a non-rotating black hole, something incredible happens. Here, the geometry of space-time allows light to orbit in a perfect circle. That boundary is the photon sphere. The photon sphere isn't a solid surface, it's a region of unstable balance. If a photon moves slightly inward, it'll spiral into the black hole forever. Move slightly outward, and it escapes into space. It's a razor-thin edge between falling and fleeing, the cosmic tightrope of light. The idea comes straight from Einstein's equations of general relativity, and it tells us just how dramatically gravity bends space-time near a black hole. The fact that light, which always moves in straight lines, can orbit at all shows that straight, in curved space, is a lot weirder than our intuitions suggest. If you could somehow stand near a photon sphere, ignoring the fact that you'd be vaporized instantly, the view would be mind-blowing. Light would curve around you in all directions, so you'd see the back of your own head, literally. Every direction would show warped and duplicated images of the universe. The sky would look like a shimmering, distorted ring of light, the gravitational lensing effect taken to its ultimate extreme. In fact, this is the origin of the bright ring we see in real black hole images, like the one captured by the Event Horizon Telescope in 2019. That glowing outline isn't the event horizon itself, it's the photon sphere, illuminated by light orbiting just before falling in. For a rotating black hole, a Kerr black hole, things get even wilder. The photon sphere isn't just a single ring, but a warped, spinning region with different orbits for light moving with or against the black hole's rotation. Space-time itself is dragged around by the spinning mass, twisting the paths of light into spirals. Photons can orbit in complex, tilted trajectories, creating layered rings of light that produce the warped, luminous halos scientists call the black hole shadow. These effects are so intricate that they form the fingerprints we now use to measure black holes' spin and shape. But the photon sphere isn't just a curiosity, it's essential to how we see black holes. Since no light can escape from the event horizon, what we actually observe comes from photons orbiting or scattering near the photon sphere. The glowing ring in every black hole simulation, movie, or telescope image comes from that region. The photon sphere defines the visual edge of the black hole, the boundary between what's visible and what's lost forever. Without it, black holes would be truly invisible. Interestingly, the concept of photon spheres isn't limited to black holes. Any extremely compact object, like a neutron star or a hypothetical boson star, can have one if it's dense enough. But those spheres are usually inside the star itself, making them impossible to observe directly. Only black holes have photon spheres that sit outside their surface, where light can orbit freely, if freely is the right word for being trapped by gravity. Studying the photon sphere helps physicists test Einstein's general relativity in its most extreme regime. The way light bends, orbits, and escapes tells us about the geometry of space-time and the nature of gravity itself. Deviations from what relativity predicts could hint at new physics, maybe clues to quantum gravity, or evidence that black holes aren't exactly what we think. Every photon that circles a black hole carries information about the laws of reality pushed to their limits. And there's a poetic side to all this too. The photon sphere is a place where light, the ultimate symbol of freedom and speed, becomes trapped, dancing on the edge of darkness. It's a reminder that even light, the fastest traveler in existence, can't always escape gravity's pull. But in doing so, it creates something beautiful, the glowing rings that let us see the invisible. Every black hole image, every shimmering halo, is born from light that refused to fall quietly into the dark. So what is the photon sphere? It's the borderland between visibility and oblivion, the place where light circles eternity before surrendering to the black hole. It's a cosmic paradox, motion without escape, illumination born from darkness. And in those fragile orbits of light, we glimpse not only the power of gravity, but the strange, poetic symmetry of the universe itself, where even at the edge of nothingness, light finds a way to shine.